video, let us study about Gaussian bivariate random variable. Correlation. Correlation equation is given by for the Gaussian bivariate random variable Z1, Z2 is given by expectation of Z1, Z2, that is under the double integral. We need to integrate Z1, Z2 PDF with respect to Z1, second time with respect to Z2. Let us substitute the PDF for the bivariate random variable for Gaussian distribution, and when we substitute, we will be obtaining the equation as shown here. And let us make a small change here. So let us put U is equal to Z2 minus rho Z Z1 divided by root of 1 minus rho Z square. So Z2 is given by root of 1 minus rho Z square U plus rho Z Z1. So when you differentiate this with respect to U, you get dZ2 is equal to du root of 1 minus rho Z square. Let us substitute Z2 and dZ2 in this equation. We will be getting the equation as shown here. And expectation of Z1, Z2 will be the integral of Z1 e to the power minus Z1 square by 2 divided by 2 pi integral of minus infinity to infinity in the bracket root of 1 minus rho Z square U plus rho Z Z1 e to the power minus u square by 2 du dz1. For the odd values, you know that gamma functions this will be 0. So we need to consider only the rho z1 e to the power minus u square by 2. So let us do that for e to the power minus u square by 2 here. So when we do it, it gets simplified as rho z divided by root 2 pi integral of z1 square e to the power minus z1 square by 2 dz1. We'll apply the gamma functions and this will reduce to the form this is equal to rho z. In this case, the correlation coefficients and the covariance are all equal. So therefore, we can write this as expectation of Z1, Z2 is equal to covariance of Z1, Z2, that is equal to correlation coefficient rho Z. We'll move on to the next topic, that is sum of two independent random variables. Let us obtain W, which is a new random variable, which is the sum of two random variables x and y. If the means and the variances of the random variables x and y are known, we can make use of linearity properties of the expectation operator, and we can write this as expectation of W, that is nothing but mean of W, is equal to expectation of x plus y. So applying the principle of linearity, we get E of W is equal to mu W, E of x is mu x, E of y is mu y. In the same way, let us compute the variance. Sigma W squared is equal to expectation of W minus mu W whole square. Let us substitute W as x plus y and mu W as mu x plus mu y. Then we substitute and we can simplify this further as expectation of x minus mu x whole square plus 2 times x minus mu x y minus mu y plus y minus mu y whole square. Expectation of x minus mu x square is sigma x square. Expectation of x minus mu x y minus mu y multiplied by 2 is 2 times covariance of xy plus the expectation of y minus mu y square is sigma y square. If covariance of xy is equal to 0, it means that they are uncorrelated. Then x and y are independent random variables, that means they are uncorrelated. So therefore, covariance of xy is equal to 0. So this reduces to the form sigma x square plus sigma y square. Let us now compute the cumulative distributive function for the random variable w. Fw of w is the probability of x plus y less than or equal to w. Let us consider a region where x plus y is less than or equal to w as illustrated in this figure, and the probability of x plus y less than or equal to w is the probability of xy belonging to that region R. That is integral double integral of fxy, that is the PDF, with respect to x and y. We need to integrate with respect to x and y. Let us make the necessary substitution here. The integral of minus infinity to infinity. The y value will vary from minus infinity to w minus x. So therefore, after substitution, we get Fw of w is equal to integral of minus infinity to infinity fxy x comma w minus x dx. As x and y are independent random variables, we can write the PDF Fw of w is equal to integral of fx of x, fy of w minus x dx. Similarly, we can write Fw of w is equal to integral of minus infinity to infinity fy of y, fx of w minus y dy. Now this is convolution integral. So therefore we can write that Fw of w, that is the PDF of w, is the convolution of fx of x with fy of y. Since the PDF for the random variable w is equal to xy, x plus y is the convolution of the PDF for x and y, we can write the characteristic function f phi w of j omega is double integral fx of x fy of w minus x dx e to the power j omega d omega. We interchange the order of integration, so we get that integral of minus infinity to infinity, this fx of x is brought here, and so integral of fy of w minus x e to the power j omega w dw. So let us change the variable w minus x as v, and let us simplify this. We get this as integral of fx e to the power j omega dx, integral of fx of x fy w minus x e to the power j omega v dv. So therefore we have phi of omega, phi w of j omega is equal to phi x of j omega multiplied by phi of j omega. We solve some problems. Example 1. Two zero mean Gaussian random variables x and y, which means mu x and mu y values are 0, are added. So W is obtained by adding two random variables x and y. Their variances are sigma x square equal to 3 and sigma y square equal to 7. The characteristic function of W is given by exponential j omega mu x plus mu y minus omega square sigma x square plus sigma y square by 2. Here sigma x square is 3, sigma y square is 7, mu x and mu y both of them are 0. It results in exponential of minus omega square 10 divided by 6. This is the second example. Let the random variable x be exponential and is given as PDF is defined as fx of x is equal to lambda e to the power minus lambda x for x value greater than or equal to 0, and it is 0 for x value less than 0. We know that the mean value is mu x equal to 1 by lambda and variance sigma x square is equal to 1 by lambda square, and the characteristic function phi of j omega is defined as lambda divided by lambda minus j omega. Let us define a new random variable w, which is the sum of x1 and x2. So Fw of W is given by the PDF is integral of 0 to W lambda e to the power minus lambda x lambda e to the power minus lambda W minus x dx. So this gives you lambda square W to the power minus lambda W, that is W greater than or equal to 0, and it is less 0 for W less than 0. And the characteristic function of the Argand random variable of order 2 is defined as lambda square divided by lambda minus j omega whole square. Thank you. In the next video, let us solve some problems on Gaussian bivariate random variables.